Guys, I'm Willa Vaughn.
Hi, I'm Anna Jones.
Chris Crow at your service. We are the Mathematical Martians, and today we are going to be jumping into Module 2, Chapter 9, which is Geometric Figures. Without further ado, let us get on with the lesson. So I actually have to start this off with a question because I'm still learning many things. Willa, I need your help on figuring out the difference between complementary and supplementary angles.
Of course. So here we have complementary and supplementary angles here in this little definition chart. And you can see complementary angles are two angles that will add up to equal 90 degrees. And then the supplementary angles are the two angles that will add up to equal 180 degrees.
Okay.
Sorry, I was trying to get a pointer up. Guess I'm not
Yeah,
going
if
to
need
be
be, we
able to.
can use the mouse.
Yeah. Okay. So yeah, these three angles here, 1, 2, and 3, they're going to be the supplementary angles of this. They're going to be the ones that equal 180 degrees, as you can probably tell as the straight line.
Okay, and are we seeing any complementary angles?
In this one, not really. I mean, you can see a 90-degree angle is going to be a straight up and right angle, and none of these have that. So none of them are going to equal 90. They all
So
kind
in
of.
this diagram, we don't really see complementary angles. We see more congruent angles, right? Because they're opposite of one another.
Yeah, exactly. That's exactly correct.
And that actually brings up a good point. Not even just angles that are opposite of each other, but in this particular instance, there are some angles that when you have their measurement, you can actually use them to figure out the other angles. So let's say, for example, we figure out angle 7, which is actually the first one you'll most likely figure out when going through this problem. Once you figure out 7, you can immediately mark it down angle 1 as well, because it's the exact same angle as 7, and they're both being created by the same line.
Yeah, it is.
So you can use
And
some
also,
angles to figure out other angles.
And also, you can tell angle 7 because the inside of a triangle is always going to equal 180 degrees. So you could do the math to figure it out as well.
Yeah, so the interior angles, they're gonna be they're gonna equal 180, so they're the supplementary. So you would do the math from 56 and 65 to get angle 7 from the 180 degrees.
That was very well explained, Willa.
Thank you. Thanks for the question.
Of course.
All right, so now I have one. I want to know, what is a vertical angle?
I'm very glad you asked, Willa. A vertical angle is basically the same as a congruent angle. They're going to be the same because they are opposite of each other.
Okay.
And as you can tell, in this diagram that we do have some congruent angles.
Yeah, I can see that the congruent ones are angle B to angle 4, just one of them off the top of my head.
Yeah. And as you can tell, we can figure out each of these angles pretty simply just using the other angles that we have.
So in this case, we're using 74 as the point C angle plus 26, which is the B angle, to help us find, I guess, point A's angle. So we're adding them together to get 180, and then we're simply using subtraction after that because triangles will equal 180.
Yeah.
Yeah.
Okay.
And you can also use angle B. I'm sorry. You can also use angle B to figure out angle 3, which is congruent to angle 1. And angle 1 is congruent to 5, 8, and 3. We just figured out 3, so we can figure out angles 5 and 8 using that same angle.
Okay.
Really helpful.
And now that you mention it, I actually notice that both angles 1 and 5 are actually vertical angles to a certain extent, because
Yes,
while
they
they
are.
are not directly facing each other like most vertical angles will, they are the same measurement and they are
Mhm.
opposite of each other, the same way that 2 and 7 are vertically opposite of each other. 'Cause
Ooh,
as you can see, both 1 and 5 are 80 degrees, as well as 2 and 7 being 100 degrees.
that is totally
Yeah.
right.
Yeah,
That was
that's a
very well
good way of
explained,
looking
Anna.
at it. Well, thanks, Anna. I know a lot more now.
You're welcome. All right, I have a question. I'm not quite sure on this one. What is the difference between concave and convex?
That is actually a pretty good question, and I'm glad you asked it. So the way convex and concave work is that concave represent it basically means a shape that has some form of curve or point in which it goes inwards. So it's kind of caving in, concave. Whereas
Okay.
convex, they are shapes that are kind of curving or otherwise pointing outwards. So the one we see here is actually concave in that the two 12y angles are pointing inwards. And the question
Okay.
we're trying to answer, we have to demonstrate how to find the measures of the angles of the concave polygon. So what we're actually going to do is we're going to use the formula n minus 2 times 180. And you might be wondering what n is. Well, n is actually going to represent the number 8. Why? Because there are 8 points around the polygon, if you count them. 1, 2, 3, 4, 5, 6, 7, 8. So now that we have n, we're going to subtract that. We're going to subtract 2 from n, 8, and then we're going to multiply that by 180. And that gives us 1080. So then what we end up doing is we will take all of these angles, these bits of the angles, so the 3y's, the 7y's, and the 12y's, and we're going to make them equal to 1080. And then from there, we simply add like terms, and like terms are the numbers with the same variables, which will give us 54y. We're going to equal that to 1080, and then we divide both sides by 54y. We cross out the ones that need to be crossed out, and then we have y equals 20. So once we have that, we simply have to plug 20 into, we have to multiply 20 by the numbers of the angles. So in this case, we have 3, 7, and y, with the subsequent answers being 60, 140, and 240.
Yeah, and it's also good to point out that another way to determine if it's a concave polygon is it's got to have at least one reflective interior angle that is in between equaling 180 degrees or 240 degrees, and the angle 12y's, they do equal 240 degrees. So that is also another way of determining a concave polygon in a more mathematical equational term, I guess.
Very well
Wow.
put, Willow.
You guys explained that really well. I get how that works now.
Well, thank you.
You're most welcome. So now I need to ask another question because I am once again confused. Well, I need you to explain to me the difference between central, exterior, and interior angles.
All right, that's a great question. So these interior, exterior, and central angles, they an interior angle is the angles that represent these different points right here on the inside, and an exterior angle is going to be these parts. And then the central is going to be the vertices that come up. This little dotted line right here is they come up to a point in the middle. And they all have different equations to get that way. So it's much like the concave polygon equation with the n minus 2 times 180, but you also divide that by the n as well. So like over here, you have 9 faces. So it would be n minus 2 times 180 divided by 9. And so that's the interior angle equation, but the exterior and central angle equations have a 360 because it's, it's the whole circle. It's not just the one angle. And so they both will equal the same answer because they have the same equation as 280 degrees in this case.
Okay.
I think it's also important to mention that the exterior angle is supposed to have a straight line coming off of it, and that is part of the angle. And it's also the exterior and the central angles equal the same, so you find them the same way.
Yeah, of course.
And that also actually, thank you for mentioning that, Anna. That helps into another thing that we need to mention. So specifically going over the specific questions so that our students understand, we've obviously, we use these formulas to find the interior, exterior, and central angles of the n-gon, but we haven't actually explained what an n-gon is. So in this case, an n-gon is a shape with n amount of sides. So a currently indeterminate amount of sides. You can count them on this to get yourself a legitimate answer when using these different formulas, but an n-gon itself is a mostly indeterminate number-sided shape. So in this case, that line actually helps in creating our n-gon here to give it its n-gon status.
Okay, that's actually really good to know where we get the n variable from in our equation.
And now you're going to hate the word n-gon.
Say that 5 times fast.
No, thank you.
Okay, so I have a really big question on this one, Anna. What are the tetrahedron subset faces?
So I'm glad you asked that, Ruben. The tetrahedron subset faces are going to be the faces of the tetrahedron inside the cube, but the most important part is that the faces of the tetrahedron do not overlap the faces of the cube. So they are not sharing the same sides or the same faces. They're only sharing their vertices.
Okay.
All right, and that brings
It's a
us
very
into
specific set of characteristics.
Yeah.
Yeah, I know. And that brings us into our 5th question. A cube with vertices A, B, C, D, E, F, G, and H are shown, and the vertices E, D, H, and G are the tetrahedron. So we can form a tetrahedron between these vertices inside the cube. And you can tell that it would take up the space of the inside corner.
Okay, yeah, that dotted line right there.
Yeah.
Okay, I see what you're getting at now.
And I think it's good to mention also that the chopped off line, that would be in the cube. So that's gonna leave behind the 4 cuts that make the 4 faces of the tetrahedron.
Right. Okay, so kind of an invisible line of sorts.
Yeah, exactly.
And just so our students understand, and so that the next question is made all the easier, what the tetrahedron is specifically, obviously it's a pyramid-like shape, but the reason that it is the way that it is because of the fact that obviously it has the 3 sides, as a pyramid does. We have 1 side, 2 side, 3 side, but at the same time, tetra actually means 4. So you have your 1, 2, 3 like a pyramid, but then you have the face underneath the shape that no one sees. That's the 4th and what makes it tetra. And that's what also causes it to stick inside a cube so perfectly, even though you can't use the faces to help make it.
Okay. That makes a lot of sense, actually.
Yeah, it's very obscure in its own way.
All right,
So
I have a
who's next?
question.
There
You kind of explained it a little bit already, but I just need a little bit more clarification. How can you tell the number of faces on a hedron shape?
That is actually a very good clarification question, Anna. So using our sixth and final question of this whole lesson, draw Schlegel diagrams for the tetrahedron, the octahedron, and the icosahedron. So what that's basically asking us is to draw the appropriate sided shapes. So in this case, we have our tetrahedron, which we've already seen. So the four sides, 1, 2, 3, 4 on the bottom. The octahedron, and of course we all aware octa means 8. So as you can see, we have 1, 2, 3, 4, 5, 6, 7. You might be wondering, well, where's the eighth? Same thing as before. It's the face underneath. If this were made in the form of a pyramid, especially the ones that we are aware of in real life, the eighth face would, of course, be the one on the bottom. And an icosahedron, as you can see, is an intimidating shape to say the least. It's got 20 sides on it. And if you count them, you'll have 19 on the top, and then the 20th is on the bottom. It would be underground, so to speak. An easy way to understand these is to look at them and think you're a bird. This is a bird's eye view of what these shapes would look like if they were real life structures. So any hedron shape, it's going to have the amount of sides that you can visibly see and then the one on the very bottom.
Okay.
Alright.
Also, a little side note, a non-mathematical way to tell the amount of sides in each hedron is using the Latin prefixes. So that would be tetra, obviously means 4 sides, as we discussed. Octa is 8, and icosa is 20. So that's for the less mathematically inclined to look. If you know your prefixes, it's a way to tell.
Very
Alright,
good.
thank you guys. I understand that a little bit better now.
Of course. And we
Yeah.
also have one more side note for all of you to learn. Take us away, Willa.
Yep. So tetra has a whole nother meaning. It is also a small tropical freshwater fish that's brightly colored, and it's native to Africa and America, and it's very popular in many aquariums.
Just your fun fact of the day from your favorite mathematical Martians.
Yep, there you go.
Looks like a goldfish almost.
Very
Silver.
nicely colored.
So, thank you guys very much for joining us for another lesson. We hope that you are a bit more familiar on geometric figures, how they work, and the different terms that you'll need to remember. Please make sure to study, and as always, we will see you for the next lesson. This is Chris Crow signing off.
Willa Vaughn, see you guys.
Anna Jones, bye-bye.